Okay, I would like to introduce our first speaker on geothermal energy, Dr. Sebastian Geiger.
Yeah, well, good morning, everyone. I'm going to talk about geothermal energy, and there's nothing better than a little pop quiz to get everyone awake. So here's my questions. My one question to you. What percentage of CO2 emissions in Europe is due to heating residential buildings? If you're online, you can put in your number as well. 62? 70? It's much lower, luckily. It's the latest data that I could find is about 17, just under 17%. If you then equate this to the global CO2 emission, it's about 1.4%. The global CO2 emissions are simply due to Europe heating its residential homes. So for every 100 tons of CO2 that we emit, 1.4 tons of CO2 is to keep European houses warm. And that doesn't include commercial buildings like hotels, universities, etc. The energy demand to heat buildings, all buildings, is roughly distributed in Europe, 2/3 for residential buildings, 1/3 for commercial buildings, public buildings. So the actual CO2 emissions are much higher. You add in Canada, North America, China, Russia, all the cold countries, and suddenly heating homes becomes a really big issue in terms of global CO2 emissions. So really, if we're serious about tackling climate crisis, reducing our CO2 emissions, one of the low-hanging fruits is decarbonizing heating. That is not to say that we need to stop working on CO2 storage, hydrogen storage. We really need every tool in our arsenal to reduce CO2 emissions. We must not forget about residential heating. And this is where geothermal energy becomes really important. It's not the only silver bullet or the silver bullet. We need to have a whole mix of tools to decarbonize heating. Some of them are really not very spectacular, like installing heat pumps, training installers for heat pumps, insulating your homes better. But geothermal energy can be really powerful tool, is a really important component. On that backdrop, I want to talk a little bit about integrated reservoir characterization for the Delft Geothermal Project. I'm going to talk a bit about what the PhD students, Kylie and Boris, are doing. They have posters here, and Guofeng is presenting his work at the Get Energy conference this week in Rotterdam. The Delft Geothermal Project is really a huge team effort. There's many, many people involved in this project. Just to highlight a few of them, there are people like Susanne Laumann, who is doing all the project management. Liliana Vargas is making sure that tons of terabytes of data become publicly available eventually, archived and stored. There are people like Dennis Voskov, Alex Danielidis have done a lot of work on the reservoir simulation side. Hemo Abels has done a lot of work on the sedimentary characterization side. Auke Barnhorn and his team, they do all the core scanning experiments, all the petrophysical data. Phil Varden is leading this entire endeavor, so it's a huge, huge team effort. It's not me who's doing this, just a very small cog in a very big project. So the Delft Geothermal Project is one project with two goals. It's to produce real energy, and it's to enable research and create new knowledge about geothermal energy. This is a picture, illustration of the Delft campus. And this is not, what we haven't done is dig big holes and then a little cars falling into these holes to produce geothermal energy. We've drilled two wells, about 2.2 kilometers deep, to target a hot sedimentary aquifer about 80 degrees centigrade hot. The wells go vertical about 800 meters, and then they kick off, and their toes are, at the toe they're separated about 1.5 kilometers apart. We've also drilled 3 monitoring wells, roughly a kilometer, a little bit less than a kilometer deep, equipped them with fiber optics to monitor seismics and have background information on the seismic data and see how the reservoir or the production of the reservoir impacts seismicity in the region. We also have funding. Phil Varden has raised funding to drill another monitoring well right in the center of where we expect the plume to be. That well is going to be about 4.5 kilometers deep, and it's going to be equipped with every bit of kit that you can imagine to see how the thermal plume is going to move through the reservoir. So there's a lot of equipment in there. It's a big research project, but as I said, It also has the ambition to deliver energy, about 25 megawatt peak capacity, flow rates about 350 cubic meters per hour. For those of you working in barrels per day, that's more than 50,000 barrels per day. It's going to heat the campus and part of the city of Delft. Because in the summertime we produce more heat than we need, and in the wintertime we would like to use some of this heat, we have also drilled 2 shallow wells, about 200 meter deep, to store some of that excess heat that we produce in the summer temporarily in the subsurface. And Martin Blumendahl, a colleague of ours at TU Delft, is leading this PUSH-IT project. It's a major European project that is piloting a number of thermal energy storage projects across Europe. What is special about the Delft Geothermal Project, it's really geothermal energy in urban environment. So not somewhere offshore injecting CO2 in a saline aquifer, doing hydrogen storage offshore. It's really in the city center of Delft. You see the blue and the injector, and red the producer, the little red dot. This is where a flat is. So we talk about public perception, safety, things cannot go wrong. Rick mentioned yesterday, if you have one CO2 project, storage project that we have, we shouldn't call it leakage, but we do have leakage, induced seismicity, that's going to cause a lot of issues. The same applies for geothermal energy. Because remember the projects that fail, we don't remember the projects that work really well. With my flat being very closely located to the injector well, so I have quite an interest of not having any ground heave, not having any induced seismicity in the project. Luckily, it's not the first geothermal well that we've drilled in the area. The license that allows us to drill, and the license actually, the license permitting was done by bachelor students back in 2007. They came up with this original idea for the Delft Geothermal Project. On the same license, a number of geothermal wells have already been drilled in the region. Closest one is in the city of Pijnack, about 5 kilometers away from the Delft Geothermal Project. Main geological settings, we're targeting the Delft sandstone. It's a lower Cretaceous sandstone, about 2 kilometers depth. On the left-hand side, you see the trajectory of the producer. On the right-hand side, the trajectory of the injector. 2.2 kilometers deep, the Delft sandstone. We have done quite a bit of logging and coring. We couldn't core the entire wells with some problems with drilling, but the entire core that we could recover is being preserved, has been scanned, is being preserved, and all the data is eventually going to become publicly available as open access data to enable future research. So what are we trying to do in terms of research at the Delft Geothermal Project? There are 3 key questions. How much energy can be delivered? How do new materials perform? And how can we best monitor a geothermal project, especially in an urban environment? In the digital twin, this little sub-project that we're working on, that I'm involved in for the Delft Geothermal Project, the aim is to help us constrain some of the geological uncertainties in the subsurface, support our decision-making process, identify which geological heterogeneities control the flow of hot water in the subsurface, and also think about how we can actually optimize data acquisition for future projects to make the right decisions. I want to talk a little bit about the geothermal twin now in more detail. So the first tool that we use in our endeavor for this geothermal twin is the rapid reservoir modeling software. And this is Kylie Baird's PhD. Kylie was supposed to be here. Unfortunately, she has fallen ill and can't attend. Last year at the summit, I talked about RM, the Rapid Reservoir Modeling platform. So this is an open source software that allows us to model geology in real time in very sparse data environments, doing things that geoscientists have always done, which is sketch over data. The data could be seismic cross-section, it could be an outcrop, could be blank screen. And then by using some geological operators in real time, a 3-dimensional model is being built as you're sketching, as you're testing your ideas. The model originally consists only of surfaces. The surfaces bound certain volumes. And here we have some idealized surfaces showing some fluvial channels, some meandering fluvial channels. We want to do some calculations. We can create a grid on the fly, and then we can do some very fast flow diagnostics to get some first-order ideas of how a reservoir could behave depending on injector producer locations. And if we want to change something, we can very quickly sketch a new model or move wells around and see how our evolution of different geological concepts could impact reservoir performance. So Kylie has used that RM framework, and she used a data set that was available from RM that contains 32 different geological models, 32 different geological concepts representing shallow marine system, different deposition environment from the Delft sandstone. The Delft sandstone is a fluvial environment, but this is more of a proof of concept study. Shallow marine systems, they contain small-scale geological features from bioturbation all the way to surf. And you see this in the brown colors, so the ancient coastline, the planform geometry where the ancient coastline was located. So 32 different models with a hierarchy of different geological structures. We assume this is a sedimentary aquifer, 2.5 kilometers deep, similar depth to the Delft Geothermal Project, temperature of 80 degrees centigrade. And then Kylie used stars to do some heat flow simulations, an injector producer pair. You see where the injector and producer are located. See here some pictures showing the thermal plumes after 60 years of production in aerial and cross-sectional view for the two different sort of planform geometries. On the left-hand side, you see the individual facies associations, so different types of geological structures, the large-scale reservoir architectures. So these are sort of the geological concepts. We can then overprint with different geostatistical models to add further heterogeneity. The right-hand pictures on these sort of green, grayish, purplish colors, these are the temperature evolutions after 60 years production for a geothermal doublet. So Kylie's run a huge number of simulations to then do a very careful sensitivity analysis that really tells us how do different geological architectures in the reservoir, how they control heat flow. And what are the most important architectures that control heat flow? So the things we really want to get right when we build a reservoir model, when we design a reservoir model, that when we think about uncertainty in the subsurface. So you see here this tornado chart, the different types of geological heterogeneities that are encapsulated in these 32 different models and their impact on geothermal capacity. So we're looking at the energy produced minus the parasitic energy losses from operating the pumps. And we're looking at a flow rate that's very similar to the production rate at the Delft Geothermal Project. So this is a proof of concept study. We now need to move this to sort of a real-world system. And the Delft Geothermal Project is located in a fluvial system. You see an outcrop here of the Bighorn Basin, which is a world-class outcrop that tells us vertically, so in terms of time, how fluvial channels interact with each other. What we don't know is, are we in a more braided fluvial system, bottom left picture, or more meandering fluvial systems, the top left picture. Where we are, braided versus meandering, that impacts things like reservoir connectivity, but also the things that are non-reservoir units, the clays, the mud stones, in a hydrogen storage and CO2 storage project, they are still part of the reservoir because they're still hot and they release heat to the flowing parts of the fluvial channels. So traditionally, and this is where Boris's PhD comes in, he has a post and can explain you all the gory details of what he's doing. So traditionally what we do is some seismic reservoir characterization, so some time slice on the top left, some cross sections. We would try to interpret where the fluvial channels are, and we can use this in the RM sense to sort of develop different geological concepts. We look at how channels are stacked and interacting with each other, if they're more meandering or more straight lines or more braided system. What Boris is trying to do is turn the question around and say, actually, we do have a set of channels, fluvial channels, how would the seismic actually look like? So he's using RM to create an ensemble of reservoir models with different channel geometries, and there's some forward seismic modeling with Eric Vasseur and his team to then see, given some overburden geometries, how would be the seismic expressions in the subsurface of different fluvial systems. So in a sense, the question that we're asking is, do we know the features that we want to look out for to better characterize the subsurface? Because we expect that a meandering fluvial system is going to have a very different heat flow behavior compared to a braided fluvial system. So this is what Boris is working on, and I'm going to come back to this at the end of the talk. And then Guo Feng, postdoc, who's, as I said, at Get Energy this week and presenting the work. So he's used RM to create a template of fluvial channels, an experimental design approach. We varied channel width, sinuosity of the channels, number of channels. And he's done some, developed a really nice technique. We can now probabilistically combine these individual channel templates to create reservoir models of fluvial geothermal system in a probabilistic sense. If we have some data, well data, for example, net to gross, then we can ensure that these models honor the net to gross data at the wells as well. And you see sort of two different examples. We just simply have varied the thickness, the width of individual channels and depth of individual channels. You can then overprint these channel geometries, these geological scenarios with different stochastic property distributions. We can change variograms, etc., to model porosity and permeability. We use GeoModPy. It's an open access, open source software that Guillaume Rongier, colleague of ours at UT in the department, has developed. So for each geological scenario, so each channel geometry, we can then also model property distributions. Then we use DARTS, Delft Advanced Research Terra Simulator. If you Google DARTS in Delft, you see a lot of pubs that have DARTS boards. So DARTS here is something different, Delft Advanced Research Terra Simulator. Dennis Voskov and his team are developing, again, open source software for modeling subsurface fluid flow processes ranging all the way from CO2 storage, hydrogen, to geothermal energy. On the left-hand side, you see a 3D permeability model with a thermal plume. And then you have on the right-hand side, on the top, you see sort of the thermal distribution in plan view and a pressure distribution in plan view as well. So now we have a framework for the geothermal, the digital twin for the Delft Geothermal Project available. We don't have data yet, so we're getting ourselves ready to when the first data becomes available. We expect that data to become available late in 2025 when the heat network is upgraded and we start producing heat. So the geological modeling in RM framework, conceptual modeling, but also probabilistic modeling in terms of combining different templates for fluvial geometries, fluvial channel geometries. You have property modeling using more so traditional geostatistics. You have geothermal simulation using DARTS. We then have an ensemble smoother approach, the ensemble smoother for multiple data assimilation to then integrate production data into this digital twin as we acquire data, and then we update our reservoir models. So what we have done at the moment, what Guo Feng has done at the moment, is simply test that framework. We have taken one geological model, treat it as the real world, so we've created some synthetic production data, and then see how we can match or simulate this production data into the digital twin. And what we're doing at the moment is playing around with different types of data. How well does the data assimilation work if you just take data from the producer, or data from the injector, or pressure and temperature data? Remember, we're also going to drill a third well into the plume. So what would happen if we use at one point the data from the third well? So here you see one example. We have a single scenario. We have the pressure and temperature data from the producer and injector. On the top left, you see the temperature data. Blue is the prior, gray curves are blue is the posterior, gray curves are the prior. The red line is the synthetic production data. Bottom left is the injection pressure. And then on the right, these two pictures are the temperature distributions at this monitoring well where we placed a monitoring well into the model. We see, so if we really struggle to get a good posterior distribution for the monitoring well, if you just take the data from the injector and producer. If you were to have data from the monitoring well as well, then we can get a much better posterior ensemble at the end of the day. Here we're just playing around with pressure and temperature data. We could equally try this, for example, with tracer data and other types of data set to see how we can constrain uncertainty. This example, we now have our first reservoir scenario. Now we simply say, well, what happens if we have a different scenario, so very different channel geometry? What happens then to our data assimilation? So if our geological understanding in terms of channel width, channel sinuosity, connectivity is wrong. Red, again, is the synthetic production data. Gray is the prior. Blue is the posterior. And we really struggle to get a good match as a result. It's not surprising. But what we hope at the end to this, and this will come back to Boris's PhD, if we do know what kind of channel geometry is more likely or less likely to be present in the subsurface based on data simulation approach, well, then we can run Boris's simulations calculate and say, well, how would the subsurface, how would the seismic data look like? Can we actually see the differences in seismic data to make better decisions about reservoir characterization early on? So to conclude, Delft Geothermal Project is really, it's a once-in-a-generation project, certainly at TU Delft, but I think so in terms of the research efforts, also probably globally. It's a huge team effort with substantial investment from the university, research councils, industry. It's a test bed for a number of research projects, a number of PhD students and postdocs. We're just sort of scratching the tip of the surface here. That's the tip of the iceberg. What you see in Kylie's work, Boris's work, and Guofeng's work. We think that this digital twin that we're developing is quite a unique approach in how we do reservoir characterization, reintegrating the seismic, probabilistic, stochastic modeling, scenario-based modeling. Importantly, all data will become open access and open source in the future. And it's also a springboard for other research projects. So I mentioned Martin Bloemendahl, who has this big EU project on piloting thermal storage, and we were just awarded this summer nearly 5 million euros from the EU and the Swiss and UK research councils to set up a consortium that involves industries and academic institutions from Iceland, Spain, France, Germany, Switzerland, the Netherlands, and the Czech Republic to first improve the way we appraise and explore for geothermal resources. Secondly, to really try to understand what's the value of data in constraining uncertainties. And third, and certainly last but not least, how we better interact with society to start building trust, co-creating a way we can actually enable geothermal energy to be developed where we need it, which is close to major population centers. With that, happy to take any questions. Thank you.
Thank you, Dr. Geiger. Questions from the floor? Microphones on both either side.
Now you're paying me back for the geology question.
Exactly. Great presentation. So you showed some results with reducing the uncertainty with the geological scenarios that you had. What method did you use for updating those models?
This ESMDA. Yeah.
What happened to the channels?
So
because that's a very famous problem.
Yeah. So this is what we need to take to look at next, because at the moment I said we're just looking at one scenario at a time. So we don't change the channels, and then we simply say, okay, now we have different scenarios, and we only update porosity and permeability within the channels. And if we don't match, then probably something is wrong with our conceptual model of how the channels look like. We want to do in sort of next 2 years in Guofeng's postdoc is to actually start thinking about what could we do to update the channel geometries themselves. But having heard yesterday about your presentation, I thought, well, we just have a different plume geometry in terms of now we have a thermal plume, not a CO2 plume. We actually use some of your technology to start training data sets to predict.
One of the challenges that we have in general in updating models using dynamic data is when you have these complex channel features, because a lot of model updating techniques are based on Gaussian assumptions.
Yes, and that was all falls down. This is what I tried to get to yesterday, as we said, we still need to have this, not just the stochastic distribution, but also the geological concept in terms of channels or dip of certain stratigraphic features, etc., which are non-Gaussian. Okay.
Okay, thank you, Dr. Jaffarpour, for the question. And I'm certainly expecting this question from Janine if she's not going to ask the question.
Hi, great presentation, and definitely I think industry leading, or maybe not industry leading, but on the forefront, because there's not a lot of work done or out there on hot sedimentary aquifers. So my question is, and maybe you covered this, was the seismic existing or did you shoot it for the purpose of this project? And secondly, have you considered or have you collected FMI data to help constrain your understanding of the braided and
so the seismic data was existing. So the Netherlands have been crisscrossed by 2D seismics. There was a huge 3D seismic acquisition project as well in recent years. So we have used existing seismic data, and no, we don't have FMI data.
Okay, I just think that would be a good thing to consider for the
Yeah.
geological concepts. Thank
Well,
you.
if ever want to fund some of the data acquisition, I have people very happily receive that funding.
Okay, so that wasn't the question I was expecting from Janine, but anyway, I'm going to ask on your behalf, or the other side of the geothermal setup, was closed loop ever considered, and if not, or if so, why pick the EGS setup?
So this is not EGS, this is not an enhanced geothermal system, because we have a lot of natural permeability.
Fractures already. Oh, so we don't have to frack.
So we don't have to frack.
Okay.
It's a sandstone with several hundred millidarcy permeability. The pressure test they've done, the well test they've done, extensive well tests, because you have water handling issues, show that the production indices are much higher than we expected them to be. So it's not an EGS system, it's just a hot aquifer. Why did we not do ever technology? I think this historically was set up to be a hot sedimentary aquifer, because here we have really good permeability, really good porosity, so big surface area where we can exchange heat. I had actually a discussion with your colleagues Janine in Germany about ever technology, and I think Daniel Merck said, at the end of the day, we want geothermal energy to work. And there's situations where, like in the Delft sandstone, where probably the sandstone is good enough to develop geothermal energy. In other situations, you don't have the porosity, you don't have the permeability, geology is not in your favor, and this wherever comes really. And so again, it's neither technology is a single bullet, we just use every bullet in our arsenal to decarbonize heating.
Okay.
I saw a thumbs up, so that was the right answer, I hope. Yep.
Yeah. There's a question on the right-hand side, sorry.
Sebastian, nice talk. Thank you.
Thank you.
I liked your picture on the sensitivity studies
Yep.
For the geology, so clearly geology is important. One question I did have is you're injecting cooler water into hot water, and we know that's a miscible displacement. It can be unstable depending on the viscosity and density differences. So have you looked at any sensitivities on the simulation side yet?
So the viscosity difference between 30 degrees and 80 degrees hot water is so minimal that there's not really, it's not steam displacing brine that we have to worry about instabilities in the displacement process. And then the thermal conduction.
There's the density differences.
Density difference is also not really high enough to get massive convection going or gravity override in these systems, because 30 to 80 degrees centigrade, we're talking about, was it 1,000 and a bit kilogram at 30 degrees versus 9 at 80 degrees kilogram, depending on salinity. So it's in that sense a really stable displacement process. Plus we have heat conduction, which is really fast compared to the advective displacement. So we're smearing out a lot of these property contrasts naturally.
Thanks.
Okay, that was Dr. Rod Badicke, president of StreamSim Technologies, who is also one of our members.
Andrew, I know you never look behind. I absolutely remiss if I don't ask the question about who's doing geomechanics. 30 to 60 is these depths and this stiffness is sufficient enough to change stress.
Yep. So I mean, I know at TU Delft you have reservoir simulators that do everything known to man. Does DARTS include like all of these geomechanical responses of the fracture system? So Hardy, please do help me out, because you work much closer with Dennis and I do, so I don't think DARTS has the full-blown geomechanics that FLAC3D has. There are PhD students who are doing a lot of the mechanical characterization at different temperatures, etc., collecting the data for the Delft sandstone. So data collection, but I don't think in some of the simulation side, it's not, there is some functionality in DARTS, but it's not as advanced as some other geomechanical simulators. But it's on the radar. So that's why I said we're really just at the tip of the iceberg here to the large number of PhD projects working in the background.
So that was Dr. Rick Charlotonic, my alumnus from the University of Alberta. I have to get a question online. From Amadrisa Shoje, The question was, do you experience any scale precipitation problem during the injection/production cycle?
Because we haven't started producing yet, so there is haven't observed any scaling, but I do believe, but I need to double check this. I think that, so the calculation, the estimations that Phil and his team have done, so there's not much of, they don't expect much of the scaling issue, but I think Eric, you're Mr. Scale. I don't think for that temperature range, it's not a big, yeah, because in that sense, it's a closed chemistry system.
Okay, so one last question. Actually, we've gone past the time, but quickly, one last question. Thank you.
Following actually a rich question about geomechanics. So one of the question about this type of saying that looking into the permeability, super high permeability, is sand production. So we know that in the Gordon projects in Australia, you just stop the projects because the sand production blocks it. So have you looked into that? And
no, but again, I think so. All the data that we have is that the Delft sandstone formation itself is stiff enough that sand production should not be an issue. But that's, as I said, we're starting producing at the end of next year, and certainly the first surprises will come, and then can happily report back of all the things we've discovered.
thank you.
Okay, once again, we thank Dr. Geiger for